manuscript. It's a review, but I didn't have a single slide. And I had to do more than just cobble the figures together. So it was a lot more work than I expected. The title is Revisiting and, most critically, Revising or Revision of the Nature of Water Speciation in Hydrous Sodium Aluminosilicate Glasses. Bjorn insists that I don't call them albite glasses. He says, because once it's hydrous and it's a glass, it's not albite. And technically, he's right. So I had to excise albite from this gigantic manuscript. It must have been like 100 entries. The funny bit about this is when Mike first came on board as director, I went to talk to him about things where I was interested at the time, and I told him about, I'm working on water in albite glasses, and he gave me the funniest look, and he said, don't we know that already? I said, we thought we knew it, and that's the point of the talk. I also want to highlight Carolyn Beaumont. She was an integral part of this project, and a high school intern who synthesized all of the glasses. She did all of the infrared measurements, made the little glass wafers, and was absolutely a superstar. She totally competent on her own to run the piston cylinder. Even when Bjorn was out of town, I remember, oh, we need this one composition. I don't know how to run the piston cylinder. And she goes, oh, I can do it. And so she competed this at the Regeneron Science Talent it used to be the Intel, now it's the Regeneron. And she got 5th place. So she won $90,000 for her summer research project. And not surprisingly, she's an undergrad at Harvard. So really incredible person, and she's going to go far. It makes me very optimistic for the future, seeing people like Carolyn Beaumont. So I don't have to tell many people in this room how profound the effect of water is on the properties of silicate melts. And so these are two really quite old papers, Shaw and Burnham over here, and this was Lebedev and Kitaroff. And basically, increasing water content from dry up to 11 weight % can change the viscosity by 7 orders of magnitude, which is incredible. Similarly, you'll have a 4 order of magnitude change in conductivity. So these are, water is probably the most, water content is the most fundamental thing guiding the properties, physical properties of silicate melts. I just want to give you a quick definition. So I might talk about Q species a little bit. This is just the vernacular people use in silicon-29 NMR. Basically, Q4 has no non-bridging oxygens or 4 bridging oxygens. Q0 would have 4 non-bridging oxygens on the tetrahedra, right? Or no bonding oxygens. I'll introduce magic angle sample spinning, but periodically you'll just see MAS. So that's what that means. And when I say static, that means no spinning. It seems obvious, but I figured I'd spin it out. And I'm only talking about solid state NMR. So I'll just refer to it as hydrogen NMR, deuterium NMR, whatever, but it's always solid state. Okay. So what does water do in a silicate melt? It, in principle, is the simplest thing. So here you have the silicate melt. Water can just simply dissolve into the silicate melt as water. Or it can hydrolyze the silicate melt, forming cyanols. So this is polymerized. It can depolymerize it. And so there's expected to be an equilibrium between water in cyanol groups and water in just molecular H2O. And it's expected that this will be a function of total water content. And so what you'd like to know, and what you need to know, is how much of the water is H2O and how much of the water is cyanol as a function of total water content. So the only game in town, if you want to do this in situ, and we do, because we're dealing with glasses quenched from melts, is using molecular spectroscopy. There's 3 regions of the electromagnetic spectrum that could potentially help here: microwave, infrared, and nuclear magnetic resonance, as I'll show you. Microwave is going to be useless in a solid or in a dense liquid state because you'll broaden all the transitions. And you'll see absorption, for sure, but you won't be able to say anything about speciation. Infrared, you have the fundamental stretching modes and wagging modes that may be able to distinguish these 2 species. And I'll show you nuclear magnetic resonance. You have what we measure is called chemical shielding. And that has the potential to distinguish those species. So infrared, the primary distinction is based on vibrational frequencies and in principle the stretching modes. And the question is, can you distinguish H2O and cyanol from that? If, again, this is irrelevant to the current thing, but in the dilute gas phase, you probably can. Because if you have no line broadening, there'll probably be a slight shift. In liquid phase, no. The hydrogen bonding just broadens all the lines. Everything's overlapped, so it's useless. In the solid state, the same is true, in fact, even more so. So the fundamental stretching modes cannot be used to distinguish these 2 species for quantitation, or even at all. So here is a thick glass plate of hydrous sodium aluminum glass. And what you see is a very saturated infrared spectrum because this is 100 microns. And if you wanted to get a good infrared spectrum in the mid-infrared, you'd want to be less than 10 microns thick. But you can see the primary OH stretching region here. This is a wagging mode there, water. And, but you can see it's very saturated. Now the near IR, because it's so saturated, you can see there's some little things going on in the near IR region. And if I blow that up, what you see is peak A, B, and C at 5200. Caffeine's got me wiggling, sorry. 5200, we'll call A, which has been ascribed to H2O. B is a 4500 band, and it's been described as cyanol. And these are thought to be what's called combination bands. And when I say thought, it's because there's no way you can prove what these things are. But I'll tell you. So the question is, what is the near IR combination band? Well, it turns out if you have a frequency, let's say for a wagging mode for the cyanol, let's say 920 inverse centimeters, and you have a fundamental stretching mode for OH at 3600 inverse centimeters, if a photon comes in that equals twice the sum of those two energies, you may create a combination band. So that's the way it goes. But it turns out if you do a principal harmonic analysis, you won't be able to predict combination bands. And in fact, they're probably related to these sort of anharmonic effects that are complicated and are not really predictable a priori. So in any case, the proposed assignments for the 4500 bands are this. If you combine the 3600 band with this wagging mode, you get a 4500. And Schultz, back in 1960, was the one who made this discovery and said, aha, this is going to work. And he noted that in muscovite, he only saw a 4500 band. And we know that that's just cyanol. Now, in opal, he saw a 5200 band, and he imagined it was a combination of these two vibrational modes. And it's true, you only see a 5200 band in opal, where all hydrogen is in the form of molecular water. So NIR spectroscopy apparently solved this problem and has been used ever since to derive this. But I highlight Zerubin, who wrote a very critical paper in 1999 that is largely ignored by absolutely everyone, did not agree with these assignments at all. And he went, and it's a difficult paper to read because English isn't his first language. And so I had to read it and read it and read it and read it until I figured out what he was trying to say. Absolutely. Interrupt at any time. So that is the definition of a combination band. That if you have, for example, so you have a cyanol group, and at 3600, light at 3600 inverse centimeters, you'll excite the stretching mode. And at 920, at a much lower frequency, you'll excite a wagging mode. And those are harmonic modes, and they're expected. The definition of a combination band is, and you'll find this in fundamental texts of infrared spectroscopy. The thinking is, in the same way that you can, it's different than a double quantum transition, right? A harmonic. Those are understood fairly well, although in principle they're forbidden transitions. Combination bands, that's their interpretation. They see them, but I should tell you, in the text that I read, that went deep into the physics of combination bands, at the very end of the discussion, the author said, at the end of the day, the interpretations of these bands are just interpretations. There is no fundamental physical proof that that is a combination band. So it was an interesting sort of disclaimer he threw out.
George, can I follow up on that?
Sure.
So one thing people do, observation, I agree with you. Isotopic substitution, for example, that shift, related to the reduced mass, where the reduced mass.
Yep.
And then you can see that combination band also matches. And has that analysis been done? I presume it would be.
It has. It has. And the combination bands shift in frequency when you deuterate the system, which lends support to the idea. I should also tell you about these bands. There's no debate that they're related to the presence of water. In the absence of water, there are no bands. And here's some of Carolyn's data to show exactly that point. So she made a number of hydrous sodium aluminum silicate glasses, and she looked at the growth of these bands with increased water content. And what she sees is what everybody sees, very systematic behavior. So you see the B band starts out more intense, and it sort of flattens out. The A band continues to grow and grow and grow, and everybody ignores the C band. It's just that simple.
How is the water content determined?
3 different ways. We did NMR spin counting. We used an element analyzer, and just by mass. So, and all were very correlated. So, yeah, we were very concerned about that. It was a lot of work. Actually, I'll tell you a stupid thing. I had done all the NMR, and I hadn't really, NMR is a very reliable way of doing it. If you have a standard and you can measure your signal as the number of acquisitions, you can determine the water content. So I had done all this NMR, and then I realized, I never actually did the spin counting. So I had to redo all the NMR to get those data. But we think we've got water contents as well as we can. I'll tell you another little anecdote, which is kind of cute, was, so I asked Carolyn, make glasses up to 10 weight percent. I didn't really care whether it was 1 weight percent or 1.1 weight percent. I just wanted glasses across the range. But she's a really hardworking high school kid, and so I wasn't precise enough in my language. So she would try to get them as close to 1% and 2%, and she must have gone through a huge amount of platinum in Bjorn's lab because she would work so hard and so independently, and at the end of the day, we're like, well, 1.3 would have been fine. But in any case, so they're not exactly, but we have the masses, but they're very close. And you can see now if we integrate these, we get this behavior. You see the 4500 band flattens out, the 1500 band grows, and I highlight that Schmidt, who does the same experiments on the same glass compositions, these are his curves. And so the data, we have more jumping around, and that's not related, by the way, to uncertainty in the water content. I think it's just signal and noise. We really couldn't do anything to the data to smooth it out, but the trends are the trends. And this is also identical to the first paper on the subject by Silver et al. So her curves plot right across here, and everybody shows a crossover point at around 3 weight percent. So now to exchange species concentration, you need extinction coefficients. And so here are expressions of water with regards to extinction coefficient, measured absorption, thickness, density. And if you know the total water content and the extinction coefficients do not change as a function of water content, you can arrange them into a nice little linear equation, plot x versus y, and the intercept will give you the water extinction coefficient, and the slope will give you the ratio of those 2 coefficients. So you can independently determine your extinction coefficients using this method. And this is one of the reasons why I think this method gave this method a lot of legitimacy. It's because when you plot this, you get a really nice linear slope. And people got super excited. They say, well, this proves that there's no water dependency in the extinction coefficient, and now we can get these things unambiguously from the data. And so here's another example that Zotov and Kepler did on a hydrous sodium aluminosilicate. And again, they show this interesting crossover behavior. You note that now it's up at about 6 weight percent. And I picked this specifically because I'm going to come back to it later. So needless to say, there have been probably hundreds of papers written using near-IR water speciation. It is by far the dominant method for making the determination. So the only other way to do this is solid-state hydrogen NMR. Well, I'll show you actually deuterium NMR works as well. So I have these little cartoons of water, so 2 hydrogens on an oxygen. Here's a cyanol with a hydrogen on an oxygen bonded to a silicon. And I just highlight this because I'm going to show these little cartoons throughout the talk to guide you. So I can use less words. So the primary observable is chemical shift. The chemical shift in this case is controlled by oxygen-hydrogen bond distance. It turns out hydrogen chemical shift cannot distinguish between these 2 species in the same way that the stretching modes cannot, because the overlap is just too great. But it turns out, as Eckert showed us, dipolar coupling between hydrogens can. And I'll show you how that works. So if you have 2 hydrogens which have magnetic moments of their own, and you bring them in close enough proximity, what happens is for an isolated hydrogen, it's a spin-half particle, and so you describe its states in terms of 2 wave functions, alpha and beta. But when you bring them together and they start magnetically interacting, you mix the 2 different wave functions of the 2 different hydrogens, and you create 4 wave functions. So you have 3 symmetric ones, alpha, alpha, this one here, and beta, beta, and we call those triplet states. And then you have one that's asymmetric, which is a singlet state. The singlet state only has 1 energy, so it doesn't contribute to the NMR signal. But the triplet states differ in frequency based on, he used D here, I'm using B here. It's called the dipolar coupling constant. So mu0 is the magnetic constant. The 2 gammas are the magnetic properties of the nuclear spins. Planck's constant is Planck's constant. and it's over the internuclear radius to the third power. And what that means is that dipolar coupling decays very, very quickly as you pull hydrogens away from each other. So it turns out that the distance between two hydrogens, water molecule and gypsum, is about 1.53 angstroms. And so you would calculate or measure a dipolar coupling constant of 33.3 kilohertz. And this is a big number for NMR. So the entire chemical shift range in hydrogen NMR is only, say, 5 kilohertz. And so the dipolar coupling is a very, very strong interaction, and it will dominate the spectrum. Now, if you just did a static NMR experiment with a pair of strongly coupled hydrogens, this is the line shape you're going to get. You're not going to get a single peak. You're going to get this very complicated line shape, which we call a Pake powder pattern, because Pake discovered it in 1948. And the distance between these two peaks is 3/2 the dipolar coupling constant. So as that goes up, they go farther apart. As that goes down, they come closer and closer together. So this was applied first by Eckert in 1988, and actually it was done by somebody just a little bit before that, but specifically for hydrous silicate glasses of geochemical interest. And they looked at the change in the line shape as a function of water content, and they said, you know, we think that the shoulders over here are a Pake powder pattern associated with H2O, and the center peak, we imagine, is just a silanol. It's not coupled to anything. It's just a broad line. But they did their experiments at room temperature. So then later, Reamer came along, and they did their experiments at 140 K, and there you can clearly resolve the dipolar coupling. And the key here is that water molecules will only contribute to the Pake powder pattern, where silanols will only contribute to the center peak. And so you could see how, if you fit these things, you could determine the speciation relatively simply. Now, we can't do static NMR here, and it turns out we don't want to. Well, that's not, I would like to do it, but we don't have, you need a very special probe for that. So what a lot of people do is called magic angle sample spinning. Now, here's an example. These are both simulations, and they're exact simulations, I should say. NMR is nice because you can solve the quantum mechanics of NMR without any approximation. So you can't do that in infrared spectroscopy. There are all sorts of parameters you have to worry about, but in NMR you can solve what's called the density matrix exactly. So if you start spinning the sample, say at 4 kilohertz, you're going to break up the powder pattern into a series that we call rotational sidebands. And you'll notice also that these peaks, these center peaks, come close together. So what happens is when you start spinning the sample, that enhanced motion of the water molecule in the magnetic field will start to reduce the dipolar coupling. We like to spin at 22 kilohertz, and so this again is a simulation of rigid water, and what you'll see is that the sidebands get smaller and they move further and further apart, and the spectrum gets simpler and simpler. Now, I should note that if you have mixtures of these two, now water is contributing to the center peak and the sidebands, but the silanols will only contribute to the center peak. Yes?
What is rigid?
Rigid means it's not moving. So rigid means it's, I'll get to it because it's really important to the story. My nickname for this paper was the Mueller Report because it was like the Mueller Report. It's like I just had to dig deeper and deeper and deeper. So it turns out water is actually rigid in gypsum, which is fascinating because if you've ever worked with gypsum, it seems like a rather soft crystal. But the whole thing that holds the structure together is the hydrogen bonding of the water. So it's rigid. It doesn't move at all, or in any detectable. It vibrates, right? But it doesn't move in an NMR sense. So you can imagine if you use magic angle spinning NMR and you had standards, like for example, gypsum. In this case, I chose silicic acid, which has only OH groups and not a lot of them. Then you'll see no spinning sidebands for silicic acid. You'll see spinning sideband intensity proportional to 100% water. And so if you had glasses that had varying speciation, they would be between these two. So here's an example of that. So here's a simulation of rigid water at 4 kilohertz spinning. And here's an actual hydrous albite specimen by Simon Cohn, 1989. And what you notice is the center band is much more intense here than it is here relative to sidebands. So the sidebands are definitely telling you you've got H2O, but the intense intermediate band tells you you also have silanols that are not contributing to dipolar coupling. All right, so one of the reasons I like spinning at 22 kilohertz is because we can, but also because it really kills the dipolar coupling. So it means that if you have two hydrogens that are even 3 angstroms apart, they will not contribute to the signal. So it gives me more selectivity. because you can imagine that you might have water silanol clustering, and I would not necessarily be able to distinguish that. So this sort of puts kind of like a cutoff or a filter on what could contribute. Probably going, I just drank way too much coffee this morning. So all the glasses were made by Carolyn in welded platinum capsules, run at 1.5 GPa in a piston cylinder, quenched from melts at 100 degrees per second, starting at 1400 degrees centigrade. And all melts were always held at times for excess of 2 hours. And we've looked at whether this makes a difference recently, and we see no difference. So 2 hours, the diffusivity of water in these melts is at 1400 is pretty high. We determined water by mass, NMR, and elements analyzer. They were all on the same line, so there's uncertainty in all three of them, but they all show that we are validly, and I should also tell you that the NIR bands also tell you that, right? So you get that systematic behavior, so you know everything's happening that way. And then we did NIR measurements that I showed you on polished 6 sections of 100 microns thick. So here are NMR, hydrous NMR for sodium aluminum silicate systems, and from 1 to 10, and you can see side bands that are weaker than you would expect for gypsum, but clearly show you that you have some water there. And with Mike Ackerson, we also did hydrous rhyolite glasses, because Mike likes rhyolites. And again, you can see side bands going from 1 up to 10 weight percent. So this gets back to your question. It turns out that dipolar coupling in hydrous aluminum silicates, the waters are not as rigid as they are in gypsum. And this has fortunately been determined and worked out very, very well. So if we were to use the dipolar coupling of gypsum, which is actually what Eckert did in 1988, so I had to, as I'll show you later, I had to correct their data for this. Turns out that's not, you want to use the dipolar coupling as measured in a silicate aluminum melt at room temperature, and that's much lower than 33.3 kilohertz, it's 22.8 kilohertz. So fortunately, because of these studies, we were able to get the correct value. So it means that even in a glass, the water molecule is just kind of moving around a little bit. It's not spinning like it is in liquid water, but it's just kind of moving randomly around, and that's enough to reduce the dipolar coupling. And it's very similar to what we achieved just by spinning it really fast, right? We're, again, reducing the dipolar coupling strength. So we do the analysis for 22.8 kilohertz, and this is what we see. For hydrous sodium aluminum silicate glass, we see water goes up, and then it starts to decay, and silanol goes up, 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 up. So this was the first big wrinkle in the story, and the same is true with rhyolite, but the crossover point has kind of shifted to higher water content. The problem is this is another NMR study, also on hydrous sodium aluminum silicate glasses, done by Schmidt et al. And what they see, also using dipolar coupling, is exactly what the NIR shows. So I was like, what? So this thing, as I said, it really became like the Mueller report. So I just had to dig deeper and deeper and deeper. So it turns out we at least decided, let's see if there's some consistency in our own data. So it turns out deuterium solid-state NMR can also distinguish H2Os and silanols, who are very, very strange phenomena that I both understand but don't quite understand exactly. But it's been established and well established even before Eckert et al. In 1987. And the idea is, so we happened to, with a study with Charles Lalask earlier, we discovered that most of the water in a potassium silicate glass, let's say 6 weight percent, exists as silanol groups. And now a deuteron is a spin-1 system, so it behaves in an NMR sense exactly to a triplet, coupled spins. The physics is exactly the same. There's some details in what's going on. So you expect to see a classic Pake powder pattern, and that's what you do when you look at when you see all these little side bands. And this Pake powder pattern, by definition, has a symmetry parameter equal to 0. Now, this is governed not by dipolar coupling, but by quadrupolar coupling. And I should say quadrupolar coupling is much, much stronger than dipolar coupling. And deuterons have very weak magnetic moments, so any deuterium coupling would be wiped out. And we're doing 8 kilohertz. So all we're looking at is a quadrupolar interaction. Now, you look at lithium sodium silicate, you see a very different symmetry parameter. Eckert saw the same thing in their study of, I think it was hydrous rhyolite glasses. And digging into the physics, it turns out D2O does something very strange. A water molecule, even a rigid water molecule, the deuterons will just shift exactly 180 degrees. And they do that at a frequency that's high enough that it starts to interact with a quadrupolar interaction. And it changes the symmetry completely from eta of 0 to an eta of 1. And so we had already known from Charles Hallas' work that most of the water in this particular glass exists as H2O. So that's absolutely consistent with what Eckert told us we should see. And then the sodium silicate, as I'll show you later, is a mixture of the two. So pure cyanol, Pake powder pattern, pure water, you get this tent-like structure. So we did this on a small set of our hydrous sodium aluminosilicate glasses, and what we saw is exactly what Eckert saw. So you see the Pake pattern on the outside, and then you see this eta equals 1 peak in the center. And we decided to simulate this first using the values of speciations derived from the hydrogen NMR, and this is what we get. And then we use the speciation, apparent speciation based on the NIR, and this is what you would get from 5 to 7. And I think everybody would agree that our spectra look much more like A than they do B. So the D NMR is actually consistent with the hydrogen NMR for the same experimental lab, same people doing it. These are simulations with a very powerful package called Simpson. So then with Mike Ackerson, we said, let's take a look at silicon-29 NMR of the rhyolites. Now, silicon-29 NMR of aluminosilicate glasses is almost pointless because of all these line broadening interactions, you just get this big, broad, featureless line. But nevertheless, we looked at anhydrous, 5 and 10 weight percent. And the only thing we could see was this progressive shift in frequency. And so we decided to do different spectroscopy, normalized to integrals. And when we subtract 5 from anhydrous, we seem to be losing signal where Q4 species would be, implying depolymerization. And we get growth in the Q3 and Q2 range, implying depolymerization. In the NIR, the hydroxyls, the depolymerization reactions stop at about 4 weight percent. So going from 5 to 10, there should be no change. So in other words, the 10 minus anhydrous should look like the 5 minus anhydrous. But in fact, what we see is evidence of continued depolymerization all the way out to 10 weight percent. So that's consistent with what the hydrogen NMR says. It's consistent with the deuterium NMR says. It is not consistent with what the NIR say. So it turns out, you know, when you start to suspect there's a discrepancy, and I was starting to think that there was, although I was really confused about why Schmidt's data looked good and our data didn't, but our data is consistent with itself. So you really start to question yourself, and you know, you start to really wonder, if there's a problem here, why I'm the only person who seems to be bothered by this, right? Everybody else seems perfectly happy. And so, you know, I really started digging through the literature, and I read every single paper I could find on the subject. And I have on the floor of my office still, because I'm a very tactile person, I have a stack of papers like this thick, and I have to keep going through them. So it turns out there was a very interesting, quietly written paper by Yamashita and Behrens in 2008. And they did a very systematic study looking at hydrous sodium silicate glasses going from composition NS6 down to NS8. And what we mean by NS4 is 1 sodium oxide, 4 silica oxides. So, and they noticed that there was this very strong relationship between extinction coefficient and degree of depolymerization, or the number of non-bridging oxygens. They proposed that this may be due to hydrogen bonding because, as I'll show you later, it's well established that the sodium silicate, hydrous sodium silicates have very, very strong hydrogen bonding interactions. But the issue was, my very first foray into hydrous glasses using NMR was with Bjorn, and we studied exactly this system from NS2 to NS8, and we saw no difference in the hydrogen bonding at all. So we concluded, at least I conclude from that, that this is entirely related to a net change in non-bridging oxygens over tetrahedron. And there is no physical explanation for why that would be the case, other than the structure of the glass has some control in the extinction coefficients in some deeply complex physical way that we can't model. But the issue, stranger than that, was that we know that increasing the water will change NBO over T as well, right? And yet everybody else was saying, no, the extinction coefficients, you know, they're unaffected by the addition of water. And that seemed really odd to me. And I will tell you also, there's a really nice paper by Olhurst and Behrens and others that looked at systematically from rhyolites to basalts and also see the systematic reduction in the extinction coefficients of water. But nobody's got an explanation for this. But it turns out Yamashita and Behrens also did they did rigid hydrogen NMR, and realized that the hydrogen NMR was giving them way more Cyanol than their NIR data was telling them. And they are really good physical chemists, and they said, we can see nothing wrong with the hydrogen NMR, so there must be something wrong with our assumption that the extinction coefficients are independent of water. So they used their hydrogen NMR to correct their data, and so the red curve is the corrected data. This is just the classic sort of if you assume the extinction coefficients are not a function of water, and that saved the day for them. But it actually created a big problem because one of the most attractive things about this is that this linear relationship proves that the extinction coefficients are not a function of water, and yet their correction is also perfectly linear. It's just that now the slopes and intercepts really don't meet anything unless you've got these correction terms, which you can only get from hydrogen NMR. So this paper is kind of sweet in a way, because I think Yamashita realized there was a real problem here, but he was really concerned about causing trouble, which evidently I'm less concerned about. And so he wrote the paper so quietly that you have to go through it very carefully to realize what he's saying, which is basically anytime you want to determine what water is doing, whether you use the NIR method or not, you're first going to have to do hydrogen NMR to calibrate it. But it was out in 2008 and ignored in probably 2008. So now, I'm trying to slow this down because I know I'm probably going a million miles an hour. So it turns out, working with Charles Alask, well, I already told you, introduce you Zarubin, who was very, very, very critical of the NIR band assignments. And but most significantly said, well, even if these were right, this will completely fail in any system that has strong hydrogen bonding interactions. Now, in all fairness, it turns out that, I think I showed you this before, in hydrous sodium aluminosilicate oxide systems, there's not a lot of hydrogen bonding. And Ed Stolper noted this back in 1982 and said, so at least for the aluminosilicates, hydrogen bonding is not a problem. But for these alkali silicates, the hydrogen bonding is enormous. So it shifts the entire fundamental stretching mode almost all the way down into the silicate region of the infrared spectrum. And now, as I said, we did hydrogen NMR with Charles on lithium, sodium, potassium, and many people have studied particularly the sodium system, and one of the things that's peculiar about it is hydrogen speciates into two peaks. Now, the blue peak, what I'll call the low-frequency peak, sits exactly where hydrous sodium aluminosilicate oxide is. So that's shared by both these systems. But this red peak, what I'll call the high-frequency peak, is basically as high a frequency as a hydrogen can go in NMR spectrum. And it's interpreted to be due to enormous hydrogen bonding. Basically, you're just pulling the hydrogen away from the oxygen. So in sodium silicates, you see both. And in potassium silicates, you really just see the high-frequency peak. And through a number of analyses, and I also showed you the deuterium wide line, that is presumably almost all Cyanol. In lithium, it goes the other way, and almost all the water is in the low-frequency peak, and the deuterium NMR shows you that that's H2O. So here is the infrared spectra, and you can see that the degree of hydrogen bonding in the Cyanol region is huge compared to most of the water in the lithium-sodium silicate. Now, these two peaks are what are used to produce that little peak, the 5200 band, if it's a combination band. And in this case, the 5200 band actually looks quite genuine because this wagging mode is very, very strong. And I should tell you, I'm not an expert on combination bands, but I've read about them. Like harmonics, double quantum vibrational transitions, you have to hit the systems really hard if you want to get a combination band at all. And so these two would be good candidates for the 5200. There's nothing obvious in the spectrum that would yell out about the 4500 band. So you can see that by the time you get to potassium, all the Cyanols are very strongly hydrogen bonded. And Zarubin's argument was, if that's the case, then any combination band you could make would be completely flattened out, and you wouldn't see it. So you'd only get a fraction, whatever combination band you detected would be just a fraction from the little bit contributing at the high frequency end. So we said that in our analyses previously and others, we think that this high frequency peak is mostly silanol. This low frequency is mostly water. And that seems to be supported in the sidebands. You see the sidebands for this peak are quite intense, but the sidebands for this peak are quite weak. It turns out a former postdoc, we published a paper on a slightly different subject, which is really wild, actually, on intramolecular deuterium hydrogen fractionation in silicate melts. I gave that talk at Smithsonian. I remember you were very surprised that was the talk I gave, but that's what I was doing at the time. So she took apart the wide-line deuterium NMR spectrum into contributions from the low frequency and the high frequency and this little sharp thing. And what you see is this peak here is clearly showing you the eta equals 0 behavior. So it's saying mostly silanols. And the low frequency peak is giving you this symmetry of 1, so it's mostly H2O. So Zarubin's point is this high frequency peak is not going to give you any combination bands. So any combination bands that you do get is going to be only from the low frequency end. So this actually came to me last week. All of a sudden I realized that Zotov's data don't make any sense for his hydrous sodium aluminum silicate systems. His are in dashed lines. This is Silver's data on her hydrous albite. I told you the crossover point shifts. And so he's detecting, or he's measuring these combination bands. They are there. I mean, nobody's making this up. They exist. But his analysis would suggest that actually you have more silanol in NS4. And the NMR says, yes, you do probably, but you can't see it in the combination bands because of the hydrogen bonding. So I can't give you an explanation about what's going on other than what Zarubin's been saying is, while the 5200 band looks like a reasonable combination band, the 4500 band may be much more suspect. Okay, so now this is a really busy slide. So getting back to the NMR discrepancy. It turns out that people have been studying, as you noted, Mike, hydrous sodium aluminum silicate glasses with NMR for over 32 years. And so it's kind of funny for me in 2020 to be writing a paper about this because it's so well trodden. But everybody uses a different method. We're all using dipolar coupling to say something, but I'm at 22 kilohertz, Schmidt static, Zavesky is static, Eckert was at 8 kilohertz MAS, Cohn was at 4 kilohertz. And so all the spectra are going to look different, right? They're going to have different size bands, this, that, and the other thing. And I wanted to just put them all in one common reference frame. So what I did was I converted everybody's data to as if we all did 22 kilohertz magic angle spinning. And in this particular case, this dashed line, if any one of these points hit the dashed line, you would have 100% water. And if it hit the floor, you have 100% silanol. And so now I can look at everybody's data in the same reference frame and see is anything interesting going on. And the first thing you can see is they're all over the map, right? Cohn's down here, we come up like this and down like that. Schmidt goes this way, which is what the NIR would suggest you should do. Zavesky is like Schmidt, but he's at some lower level. And here's Eckart's data, which had to be corrected for the fact that his standards weren't actually the dipolar coupling that you actually have in the aluminum silicates. And he only had 3 data points, but it suggests that he's seeing this sort of rollover behavior that we clearly see. And perhaps Cohn only had 1 data point, so that's all we could do. Yeah. Sorry about that. God, I hate myself when I do that. That is the sum of the side bands ratioed to the center band. Center band. So when that ratio is 0.17, then you would have 100% water. And the nice thing about NMR is we can determine that exactly. It's not an interpretation or anything. If it's 22.8 kilohertz, and you're spinning at 22 kilohertz MES, that's where it would be. So this wide variation is, and I went through the analysis of every single person's experiment. I'll show you. And I asked myself, well, maybe there's just something fundamentally wrong with the NMR, right? The irony of this talk is I'm telling you, suggesting to you there's a problem with the NIR, and yet when everybody does the NIR, they see exactly the same thing. It's super systematic, and why is there a problem? Which is one of the reasons why it's so popular. And then I'm telling you that NMR is a really good method, but I'm showing you the data are all over the place. So the first thing we worried about is, an external, any external issues. With static NMR, you need special probes, you need really short delay times, and if you don't do that right, you can artificially enhance the amount of Silanol that you think you're seeing over water. However, everybody who does the static experiments knows exactly what they're doing. They have perfect probes, great NMRs, and there's no errors that I can see in there at all. The other thing is that maybe you just don't have enough pulse power, in which case you might enhance sort of a narrow peak over a broad peak. But again, everybody's working with very really good solid-state NMR. They know their business, and that's not a problem. Then there's internal issues, like, well, what if you have hydrogen clustering? Particularly of cyanols, that might give you a higher H2O because dipolar coupling is dipolar coupling. It turns out there was a study by Roberts et al. Where they specifically decided to look for clustering, and they saw no evidence of clustering in a hydrous sodium aluminosilicate glass. So this is why it's a good system to study, because it's rich in data. Similarly, increased water mobility could change the dipolar coupling, and if that's happening, that's going to enhance what I think I'm seeing in Silanol groups. Fortunately, that's been studied as well by Schmidt and Reamer and others, and there's no evidence at all that water becomes more mobile from, say, 1 weight percent water up to 10 weight percent water. And then the last bit is something everybody worries about, which is what we call differential T1 saturation. And without going into details, it's possible that hydrogen in water might relax a little bit faster than an isolated Silanol group. And if that was the case, you'd think you'd be detecting more H2O than you actually are. But it turns out every single study, including our own, we know this is a possibility. We measure our T1s. The T1s, the delay times to account for them are perfectly fine. So I cannot find anything in the NMR that would discredit any of these other data. And so you can imagine I was really confused. And I just had to think about it. Again, it's like the Mueller report. I'm like, I'm missing something here. What am I missing? It's just how can the NMR, which just seems to be a perfect technique, and it's physically simpler than the NIR, and it gives me data all over the map, right? So it turns out there is a systematic thing that I hadn't thought about, which is how the glasses are made. And there's some big differences. And so it turns out we and Cone used a piston cylinder apparatus, and the quench rates there are really fast. So you drop temperatures about 100 degrees per second. Turns out that Schmidt and Zawalewski, they used an internally heated pressure vessel. And the fastest cooling rates they could get were about 100 degrees per minute. So it's almost 2 orders of magnitude in quench rate. So that may explain what's going on here, because as I'll show you, quench rate has a big effect on the glass transition. And the other bit is that it turns out Zawalewski synthesized in this range his glasses at 500 bars. And Schmidt was at about 5,000 bars. And Eckert and ourselves were up at about 15,000 bars. So there is systematic variations in the experiments that may, I can only say may at this point, reflect the differences that we see in the NMR. And if that's the case, there's some interesting, that would mean that the equilibrium between, say, Silanol and water is such that at higher pressures, molecular water is favored over Silanol, and at lower pressures, Silanol would be favored over water. And there are some physical chemical reasons why that would be reasonable. So, as I said, the structure of glass, this is an assumption, but it's a pretty good assumption, is the structure of the melt at the glass transition. So it's melt, 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 and then it freezes in, and that's where you go. And so Dingwall and Webb did a very substantial analysis that I think is still cited a lot to this day, that of course the glass transition is going to be a function of the quench rate. So he's plotting time over 1 over t. This is just a schematic, but if you quench really, really fast, 1 over t gets very, very small, and your glass transition will be here, but if you quench really slowly, the glass transition will go to much lower temperatures before you lock in the structure. And nobody disagrees with this analysis. And in fact, 1 year before he came up with this analysis, Ed Stolper also said, yeah, and the glass transition temperature should also be a function of the water content, which nobody disputes. So one of the things that Dingwall and Webb pointed out, which I don't know how well appreciated it is, but it should be, is that any time you study specifically glasses, hydrous glasses, as a function of water content, that is not an isothermal experiment, right? Because every one of those water contents is actually giving you a glass structure at a different closure temperature. And that's just what you're stuck with. You can't beat that game. You can't quench fast enough. no matter what you do. So I thought to myself, okay, so I went to Dingwell and Webb's paper, and using our 100 degrees per second and some analysis he had, we predict that maybe the glass transition for our glass would be about 787 K, and Schmidt, much slower, he might be like 689 K. And I thought to myself, I'm almost done, perhaps we can determine the enthalpies and entropies of this, making this assumption. So I also wanted to do it to make sure I wasn't saying something really stupid, right? Like if I ended up with like 1,000 kcals per mole. And it turns out you should get numbers that are not unreasonable. So the enthalpy is on the order of 44.8 kcals per mole. Entropy is 59 calories mole K. It turns out the NIR bands also vary as a function of temperature. And in fact, you can measure them in the melt, which is a real plus. You can't do solid state NMR in a melt, obviously. Their enthalpies are very different than ours, and their entropies are very different than ours. So, you know, these are not unusual, unreasonable numbers, but all of a sudden you realize that we really have to sort out, you know, is the NIR right? Is the NMR right? What have you. Here is the crux of the problem, though. So Yamashita had supposedly solved the problem because he was able to correct his NIR data with NMR data. But that's not really possible because here's Schmidt's curve in dashed, our curves in dots. Silver's data would do exactly the same thing. There's our NMR data in dots. Schmidt comes up in black dots, and Eckert does this. So all of us are seeing exactly the same thing when you do NIR, but all of us are seeing different things when we do NMR. So as I said, both can't be correct. Both can be incorrect, but they both can't be correct. So I laid this out, I think, because we're going through this impeachment, I decided to be lawyerly. And so the case for NIR spectroscopy is, first and foremost, the NIR bands unambiguously are due to the presence of water, and they vary beautifully systematically when you add water to it. And that's the attraction to the technique, and I think that's why people really got into it. But the case against it is pretty strong, too. As I said, it's discrepant with hydrogen NMR. Not everybody supports the idea that the 4500 peak is only OH, and Zarubin was pretty adamant that he thinks that water is also contributing. There's no way to prove the definitive origins of these peaks, so the physics of combination bands is actually very complicated, and most people say it's an interpretation. It is not proof of origin. And then there is no physical explanation for why the extinction coefficients decrease with increased NBO over T. And that's disconcerting if you can't even, the fundamental physics, you can't explain this yet. And then I finally looked at that and I said they also make no sense in the sodium tetrasilicates. That just makes no sense to me at all. The case for hydrogen NMR, the physics dipole coupling is very well known and predictable. The observation of spinning sidebands is unambiguously due to dipolar coupling. That there's no other interpretation. It does not rely or require deriving extinction coefficients. And in our case, it's consistent with what we see in deuterium and silicate-29. So the data are internally consistent. The case against it, clearly it's discrepant with the NIR results. I showed you there's a lot of variation. And then, you know, you always have to throw out, maybe there's some completely unknown effect, right? That but I've been doing NMR for 25 years. It's the thing that I do. And I think it's extremely unlikely that there's some mysterious unknown effect in operation here. NMR is very robust. So the conclusion slide is, we believe that NIR is probably unreliable for water speciation. It's probably very reliable when calibrated for measuring water contents, because it's very systematic. But for actual speciation, I'd be concerned. I think hydrogen NMR should be used, but how you make these glasses may have a very strong control on what you observe. And combining that with kinetics and quench rate dependence and equilibrium might actually be very difficult to separate those two, and will definitely complicate interpretation, in particular determination of enthalpies and entropies. So it points to the idea that many carefully designed experiments are going to be required to try to sort this out. And it also suggests that this might not even be possible. It may be that this is just an intractable problem. And so that's my talk. I got back on time. Thanks for your attention. I said this paper's been reviewed since September, and I'm not expecting to see a review soon. And we're certainly not expecting any prizes for most popular. Thank you.
Hands going up all over the place.
Lights.
Very interesting. George?